Hello everyone and welcome to today's video on continuous random variables. So from an earlier video, we learned about discrete random variables which can only take on discrete values. For example, 1, 2, 3, 4, and so on and so forth. But a continuous random variable is a variable that can take on any value given any interval. For example, I could define a continuous random variable as being able to take on any real value from 0 to 10. So not just 0, 1, 2, 3, but like decimal values too, 0.12, 5.78. Now we're going to look at the probability density function, which is called a PDF, and a cumulative distribution function, which is the CDF. The probability density function is used to find the probability of the variable landing in a specific interval, let's say from A to B. And this probability will actually be just the area under the curve of the PDF. So if you look here, the probability that my variable x lies between the interval A and B is the integral from A to B of fx. Fx is just this probability density function. Now I have one little note over here. The probability at a certain point is actually just 0. For example, let me ask, what is the probability that I'm exactly 52.5 kg? Let's just say our variable here, x, is the weight. The probability that I'm exactly 52.5 kg is actually just 0. This is because continuous random variables can take on any real value. I could be 52.49832 something kg. And that's why the probability at a certain point is just equals to 0. And as such, if you look here, it doesn't matter if it's inclusive or exclusive of these 2 points A and B over here. So the probability that my variable is strictly between A and B is also still the integral from A to B of fx. Now again, similar to discrete random variables, your total probability is 1. So your total area under this curve is just 1. The cumulative distribution function describes the probability that your variable x takes on a value less than or equals to a specific value, let's say A. As you can see here, Px is less than or equals to x. So this area over here actually ends up to be this point over here. So if this area is 0.2, this point over here is 0.2. Because the probability that x is less than or equals to A is 0.2. Now let's say we have this area over here, and we know that this probability that x is less than or equals to B is 0.7. Then this point over here, when x equals to B, we just have a y value of 0.7. So this cumulative distribution function is actually a function of the area under the curve of this PDF. As you can see, we are finding the area under a curve and plotting them on a function, which is called the cumulative distribution function. To find the cumulative distribution function from your PDF, what you're going to do is take the integral from x1, which is this original point over here where the function starts, to x of fx. Now what this could look like could be something like this. If let's say your probability density function is x squared and it starts from 0, then what this will look like is x cubed over 3 x 0, which if we substitute the value of x into x is just x cubed over 3 and then minus 0 cubed over 3. And this tells you, let's say you want to find the probability that x is between 0 and 1, we can see that this actually gives you this probability. Now let's try a question. The continuous random variable x has the probability distribution function of this thing. Now what this can be read as is a piecewise function. Over here, from the range of x between 0 and 1, the function is defined by y equals to 4k. But from the range of x between 1 and 3, my function is defined by kx minus 3 squared. Now the question first asks you, find k. Now what I'm going to use over here is the total probability is equals to 1. So the total area under this curve is equals to 1. So I'm going to take the integral from 0 to 1 of 4k, and then take the integral from 1 to 3 of k x minus 3 squared. And I equate this to 1. Now after I integrate, I'll just get this. And let me substitute all my values. I'll get 4k minus 4k times 0, which is just 0, plus 1/3 k, and we'll take 3 minus 3 cubed. 3 minus 3 is just 0. And then we'll minus 1/3 k times 1 minus 3 cubed. So if we solve for this, we get k equals to 3 over 20. Now the question asks us to find the CDF. So again, what a CDF is a function of the area under the curve of the PDF. Now for this part over here, this is simple. You remember our formula, we are integrating from the start to any x. So this is just equals to 4kx. And if I substitute my value of k, this is just 3 over 5x. Now for this part, if I integrate from 1 to x, then I'll be just getting this area over here. But the cumulative distribution function wants it from 0 because we're starting the function at 0. So we will need to add up this entire area over here. As such, the cumulative distribution function for this part is defined by the integral from 1 to x of k x minus 3 squared. And then we still have to add on this area because we're finding the probability that x is less than or equals to some value of x. And for this domain, we have to add up the area under the curve provided by our integral plus our extra triangle area. This is just finding 3 over 5 times 1. Because if we want to find the probability that x is less than or equals to 1, this is equivalent to doing this, which is also the same as saying 3/5 times 1. And this should give me 1 over 20 x minus 3 cubed plus 1. Now let's find the CDF. The CDF, again, will be a piecewise function. We know that the probability or the area under the curve over here, when x is less than 0, is just 0. So we can write this here. Then for x is between 0 and 1, we know that this has to be 3/5 x. And then we'll get this over here when x is between 1 and 3. And finally, when x is beyond 3, we know that the total area under the curve is just 1. And this right here will just be your CDF. Now let's move on to expected value and variance. If you remember, the formula for expected value for discrete random variables is just this. And you can see this is very similar, except that now it's an integral. So the expected value is the integral for all x of x times fx, where fx is the PDF. Let me bring back the PDF from earlier to show you how to find the expected value. Now the expected value will be the integral for all x. So in this case, for the first part, where x is between 0 and 1, we have x times the function. So we have x times 3/5, which is just 3/5 x. Now for the next part, where x is between 1 and 3, I'm going to have x times fx again. So it's x times this function over here. And we'll just get this. After evaluating these definite integrals, I can find the expected value. Now the next one is the expected value of gx. This is just the integral of all x of gx times fx. So if we have e of x squared here, we have 3/5 x squared and 3 over 20 x squared. Again, we're just taking fx times gx, and in this case, gx is x squared. Now the variance still has the same formula, it's just ex squared minus ex whole thing squared. The next thing I'm going to look at is how to find the median. So let's say I have the PDF fx over here. Your median m will just be this point where it splits the probability distribution function on half on both sides. So what the formula to find the median will look like is the integral from a, which is our starting value, to m, which is your median of fx, will be equals to 0.5. So let's say I have this example over here. We want to find the median for this. What I'll do is take the starting point to m, which we want to find as our median, and then e to the power x dx equals to 0.5. And if I then evaluate this definite integral, I can then find the median. Now I'm going to show you a quick way of solving this using the GDC. Now to solve for m, or the median in the GDC, I'm going to show you a little trick called nsolve. So nsolve can help you to numerically solve for any equation, even equations involving integrals. So let's write in nsolve in bracket. Now our equation is to solve for m in the integral. Come over here and click the integral button from 0 to m of e to the power of x dx. And we want this to equal to 0.5. That's the equation that we're given. Now we're trying to solve for m, so we write comma m at the back to denote that we're solving this equation for the variable m, and press enter. And just like that, we found our median as 0.405. Now finally, let's look at the kth percentile. So the median is kind of like your 50th percentile. So let's say we want to find the 20th percentile. That'll be over here, where this area is 0.2 and this area is 0.8. Similarly, something like the upper quartile, which we remember as the 75th percentile, Q3 would just be 0.75 here and 0.25 here. So this is summarized as the kth percentile, where we want to find the value of t, is the integral from a, which is our starting value, to t of fx will be equals to k over 100. Now finally, let's move on to the mode. So in terms of your probability distribution function fx, the mode is just your maximum point. And we're done. Here's a summary sheet for continuous random variables.